Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors in the Geometry of Space, Section 8, Arc Length and Curvature, Video 4, Parametrizing a Curve as a Function of Arc Length. Now, what the heck does this mean? Here's a question we're going to try to answer. Given a space curve defined parametrically, so we've got x as a function of t, y as a function of t, z as a function of t, can we redefine the parametric equations as functions of the arc length, plural? Now, why would we want to do that? Why would we want to redefine our parametric equations as, instead of f of t, g of t, h of t, redefine them as f of s, g of s, h of s, where s is the arc length function? In other words, can we derive a function that answers the following question? We got a curve in space. Where am I on this curve after I've traveled a certain distance? Because the original parametric equations answer the question, where am I after a certain time? The arc length function answers how far have I traveled after a certain time. But this function, this reparametrization, is going to answer the question, where am I after I've traveled a certain distance? So let that sink in. Originally, a function of t. Where am I after a certain time? Arc length function. How far have I traveled after a certain time? This thing. Where am I after I've traveled a certain distance? So like if I'm on this curve, if I've traveled 10 miles, where am I on this curvy path? Well, it's actually not as hard as it seems because it's really more of an algebra situation than a calculus situation. In the previous video, we found that the circular helix was given by the vector function r of t equals cosine of t, sine of t, t on the interval 0 to 2 pi. For that, the arc length was, it's supposed to be a v here. That's going to mess something up. That's what I get for trying to set this up early. But in the previous video for that space curve defined as r of t equals cosine t, sine t, and t on the interval 0 to 2 pi, the arc length was the square root of 2 pi, and the arc length function for any t in the interval 0 to 2 pi was given by s of t equals the square root of 2 times t. So give me the value of the parameter. Tell me how long we've been traveling. I can tell you how far we've been traveling. I can tell you the arc length we've traversed. But can we redefine the curve as a function of s instead of a function of t? So in other words, in the parametrization of the curve, which I'm about to highlight because it's kind of hiding in there, this tells us where I am after a certain time. Give me the value of t. I'll tell you where I am on the curve. Can we redefine it so it reads r of s so that it tells us where we are after we've traveled a certain distance? In other words, can we take out the t and replace it with something with an s? Well, in order to do that, we would need an equation that relates t and s. Well, here it is. And although this is written in function notation, s of t is equal to something in terms of t, we could just write it as two variables and write s equals the square root of 2 times t, which is still technically a function. Give me a value of t, I can calculate a value of s. It's just not written using function notation. Well, that equation gives us a relationship between what we currently have, t as the parameter, versus what we want, s as the parameter. So now it's just some algebra time. We just need to figure out what t equals as a function of s and do some substituting. So yes, we can do this. We can reparametrize the curve as the function of arc length. Translation, can you tell me where I am if I tell you how far we've traveled? Or if I tell you how far I want to travel, can you tell me where I will be? Well, yeah, if we can solve the arc length for a function of t, which we clearly did. So like I said, this is more of an algebra situation. Our original parametric vector equation, if you will, was r of t equals cosine of t, sine of t, and t. But the relationship between arc length and time was arc length is the square root of 2 times t. That came from our arc length function. If we solve this for t, we get t equals s over the square root of 2. I know some of you will go, but you have to rationalize the denominator and make it look like this. If you really want to, but there's really no benefit to that. There's a historical benefit to rationalizing denominators, and occasionally there's a theoretical benefit, but doing it for the sake of doing it is just a waste of time. Okay. All right, so now we got t as a function of s. We're just doing function composition, basically. R equals t of s. I'm sorry, what am I saying? Instead of saying r of t, we're saying r of t of s. So all we have to do is replace each t with s over the square root of 2. By the way, this is t of s. Time is a function of distance traveled, if you will. So instead of cosine of t, we have cosine of s over the square root of 2. And we have sine, instead of t, we have s over the square root of 2. And instead of t, we have s over the square root of 2. So in theory, it's really not that difficult to reparametrize a curve as a function of its arc length instead of a function of the time parameter, t, if you will. All we have to do is establish a relationship between the time traveled and the distance traveled, and that's what the arc length function does. The arc length function answers the question, after I've traveled a certain amount of time, how far have I traveled? Solve that for t, so t equals a function of arc length, and then substitute that into our parametric function. And then we get what we came for, which was reparametrizing the curve as a function of the arc length. Now, what would the interval be? Well, that's also pretty easy if you have the original interval, because remember, the original interval for t was originally in the interval 0 to 2 pi. So what will s be an element of? Well, when t equals 0, what does s equal? Yeah, look right here. S is equal to 0. When t equals 2 pi, what does s equal? Well, square root of 2 times 2 pi, or 2 square root of 2 pi. So we could even reparametrize in terms of arc length. Now, something seems a little fishy here because our original arc length was square root of 2. So why would the arc length go all the way to 2 square root of 2 pi? 0 to 2 pi was our interval, I believe. Oh, wait, the arc length was, oh my gosh, I just wrote something. Oh, because this wasn't the arc length. I'm sorry. The arc length back from the second video was 2 square root of 2 pi, wasn't it? For some reason, that's not sounding familiar. Oh my gosh, I screwed up the other video. Well, dang, now I'm gonna have to go back and fix it. That's all right. This is what happens when you make videos.